All right, I want to do several examples of calculating the area enclosed by curves. And so we've looked at the area underneath the curve, basically between the curve and the x-axis. Here we're going to look at multiple curves, usually two. We'll throw in one example with more, finding the area between those. I'm going to do four examples, I believe, and you may fast forward through parts of this as you get it and get to the stuff you really want to see, but I want to be thorough here. So the first example we'll look at is calculate the area of the region enclosed by two curves. The first is y equals 2x minus x squared, and the second one is y equals -3. Now, we know that this first curve is a parabola because of the x squared, and we know it opens downward because of the negative in front of the x squared. We're going to have to get a decent graph of these curves so we can visualize the region that we want the area of. So often a place to do that, since these two curves enclose a region, they have to intersect. So before you start graphing, it might be useful to figure out where they intersect so you know where to focus your graph. So we'll find the intersection here first. Find the intersection first. And so to find the intersection, we have to figure out where these two things are equal. And the first equation is y equals 2x minus x squared. And the second one says that y equals -3. If they're going to overlap, the two y's have to be equal. In other words, we have to solve the equation where this y equals this y, where 2x minus x squared equals -3. And so we'll solve this equation for x, and that will tell us where the two curves intersect. Now this is a quadratic equation because of the x squared, so we want to get 0 on one side. I like to make a positive x squared, so I'm going to move all my terms to the right. So this will turn into positive x squared minus 2x minus 3 equals 0. And then this quadratic equation can be solved by factoring or the quadratic formula or whatever you like. I'll use factoring because it's faster. And we get x plus 1 times x minus 3, meaning that these two curves intersect when x equals -1 and when x equals 3. So that's going to help us focus our graph of these two curves. Now, this is a curve, this is a horizontal line. So when I say curve, it's a general concept of basically any graph. So let's look at the parabola and set up an xy table. And let's focus our attention on the x values from -1 to 3. So we get -1, 0, 1, 2, 3. And this is the most basic approach to graphing, is just plotting points. If you know a lot about parabolas, you could find the vertex and you could do some fancy stuff like that. I'm not trying to emphasize those concepts in this video though. All right, so now I have to plug -1 in, and I'm going to plug these in pretty quickly because we have a lot to get through. So if I plug -1 in, I get -2 minus 1, which is -3. If I plug in 0, I get 0. If I plug in 1, I get 1. If I plug in 2, I get 0. And if I plug in 3, I get -3. So these 2 points, when x is -1 and when x is 3, should be where the two curves intersect. Now this is a horizontal line, so we'll see that that's actually true. So let's go ahead and graph our two curves on my coordinate plane here. So I need to set it up. My x values go from -1 to 3, and my y values go from -3 up to 1. So I can have my x-axis pretty high, and my x values go from -1 to 3. So we'll call this our y-axis. That's where 0 is on the x-axis. And so let's see. Let's say that this is -1. 1, so here's 0, 2, and there's 3, okay, on the x-axis. And then the y-axis, I need to go from -3 up to 1. So let's say let's use the same scale. How about that? If I can manage the same scale here. So -1, -2, -3. And then +1 is right there. Okay? All right, so let's plot some points here to see the graph. So I've got -1, -3. I've got 0, 0. I've got 1, 1, 2, 0, and 3, -3. And so our parabola, you can see it now, it does in fact open downward as we suspected, as we knew in fact. And that's the parabola. Now the y equals -3 line is just the horizontal line that runs through -3 on the y-axis. Okay? And so we can see that the region enclosed by those two curves, is this region right here. And we need to find the area of that region. So we don't need any of this anymore. Let's focus on how we would build rectangles for which we could find the area and then add the infinite rectangle areas together. So we can use vertical rectangles here because the parabola is always above the horizontal line. In fact, let's label the equations of those. That's a good practice. So the top curve is y equals the 2x minus x squared. And the bottom curve is y equals -3, the constant. Okay? All right. Now let's look at where the rectangles would be. And so all the way from -1 to 3, if we pick a rectangle that's infinitely thin, maybe this guy right here is an example, then that rectangle, we'd need its area. So we'd have the area of that rectangle is going to be, well, it's going to be the width, which is dx, because the width is measured horizontally. It's a change in x. Infinitely thin, dx. The height is going to be the top y minus the bottom y. So, and they need to be in terms of x. So the top y is the parabola, so I'll label that y with a subscript of t, and that's literally 2x minus x squared. Minus the bottom y, right? You go from the parabola down to the horizontal line, which is -3. So the height of all of these rectangles is the top y, 2x minus x squared, minus the bottom y, -3. That's the height of each rectangle. So that's the area of one rectangle. We need to add them all together, this infinite sum integral, and we're integrating with respect to x. So we need to know the limits of integration, which x values. We're adding all of these up from x equals -1 to x equals +3. And that's the integral that represents the area between those two curves. So that's usually the hardest part, is getting a graph that's workable, setting up, understanding the region that's enclosed, creating rectangles, and getting your height and your width in this particular case. Evaluating the integral should be pretty easy, and that's not what I'm here to teach you. So I'm going to pause the video and work this out. You can pause it and try to work it out as well. That way you can at least check your answer. So when I evaluate the integral, I see that the area enclosed by these two curves happens to be 32/3. So again, integral is pretty simple. The hard part is setting it up. So that's one type of example. Let's look at another. All right. So let's say we want to calculate the area of the region enclosed by y squared minus 4x equals 4 and 4x minus y equals 16. And so this one's a bit different. Neither one of them is solved for y or x. So that may be the first thing we want to do because we'd like to know the intersection, right? We want to work towards the intersection. So again, one way you can do that is to maybe solve both of them for the same variable and then use the same approach we did last time. So that's what I'll do here. I'm not going to solve for y because when I do it, I have plus or minus the square root. So I'm actually going to solve these both for x. So let's take this guy first. Negative 4x equals 4 minus y squared. And I'm going to run you through maybe a different way of thinking through the algebra here. You could certainly divide both sides by negative 4, and that would be totally fine. Okay, let's do that. Sorry. So if I divide by negative 4, this turns into positive 1/4 y squared, and this turns into negative 1. So now I've got this guy as x equals a function of y. And then this guy, solving for x, I'll have 4x equals y plus 16. And multiplying by a fourth, I'll get 1/4 y plus 4. So now I've got each of them in terms of x. If I want to find the intersection, then I want to know where, since they both represent x, I want to know where they're equal to each other. So I'll have 1/4 y squared minus 1 equals 1/4 y plus 4. Now, the first thing I'm going to do here to solve this equation, because it's quadratic again, it has a y squared, I don't like the fraction. So what I'm going to do is multiply everything by 4, because that'll cancel to 1/4. So distributing 4 on the left side gives me 1y squared minus 4, and on the right side gives me 1y plus 16. And now I don't have to worry about those fractions. To finish solving it, I'll get 0 on the right side. So I'll have y squared minus y minus 20 equals 0. And then I'll factor. You can use the quadratic formula if you desire. So I get y plus 4 times y minus 5. And so I can see that the two curves intersect when y is negative 4 and when y is 5. Okay. All right, so now let's graph each of them. So I'm going to set up an xy table for each. This is a parabola again, but it's a parabola that opens horizontally because y is squared. It actually is going to open to the right because we've got a positive coefficient. This is just a typical slanted line, a linear equation. So if I set up my xy for this guy, I'm going to have my y values go from negative 4 to 5. So that's, you got to be really careful here. I still like to have my x column first and my y column second, so I think of them as proper ordered pairs, x and then y. But I'm actually going to plug y values in and then calculate my x values. So I'm going to go from negative 4 to 5. So I might skip some of these. Let's go negative 4 to negative 2, and then to 0, and then to 2, and then maybe to 4, and then to 5. Okay, use whatever you like. And I'm going to plug those in for y to calculate x. And I'm going to do that quickly again. So 16 times a fourth is 4, minus 1 is 3. Let's see, 4 times a fourth is 1, minus 1 is 0. The same is true if you plug in 2. If you plug in 0, you get negative 1. If you plug in 4, you get the same thing as when you plug in negative 4. If you plug in 25, you get 25 fourths minus 4 fourths is 21 fourths. Okay? And this point when y is negative 4 and the point where y is 5, those should be the points of intersection. So if we set up an xy table over here, we know this is a slanted line, so I really only need 2 points, whereas a parabola you might need several. So here, I'm just going to plug in negative 4 and 5 for y. I just need 2 points, so why not use the points of intersection? If I plug in negative 4 for y, I get negative 1 plus 4, which is 3. So you can see, same order pair, it is a point of intersection. If I plug in 5, I get 5/4 plus 16/4 is 21/4. So that is the point of intersection. So that works out great. It's a good indicator that we haven't made any mistakes so far. It's not a guarantee, but it's a good indicator. All right, so now let's set up our graph. So I'm going to graph the parabola first, and my y values go from -4 to 5. So that's pretty, my x-axis is going to be kind of centered here on the page. Maybe you're like right here. That's my x-axis. And then my x values go, the smallest is -1, the biggest is a little bit more than 5. So let's say that, let's say this is -1, this is 0, so that's our y-axis. And then 1, 2, 3, 4, 5. That's 5. And we could keep going, okay? All right, then our y-axis, we need to go from -4 up to 5. So I'm going to actually use a different scale for my y-axis because I have less room. So there's -1 on my y-axis, -2, 3, -4 is right there. And I'll go up to 5, so 1, 2, 3, 4, 5 is there. Okay, so we've got our grid set up. Now let's graph the two functions. So the parabola first, 3, -4 is right there. 0, -2 is right there. -1, 0, 0, 2, 3, 4. And this is 5.25. So that's like right here and there. Okay? So this is our parabola as we talked about earlier. It opens horizontally, it actually opens to the right. Okay? So there's the parabola, roughly. And the 3, -4, and the 21/4 5 are the points of intersection. I know those are the 2 points I'm using for my line, so I don't have to plot those. I've already got them here. And I'll just connect those together with a straight edge here to kind of get a straight line. All right, so there's the line. Now that I can see where they are in relation to one another, I can label them. And I can see that the line, well, the region we want to find the area of is this region right here, okay? And so I can see that my line is the rightmost boundary, so this is going to be x equals the line 1/4 y plus 4, and the parabola is my leftmost boundary, x equals 1/4 y squared minus 1, okay? And so now we can talk about setting up this integral. And so in this case, because I've got one of my curves is the right boundary and the other's the left, it would probably make more sense to use horizontal rectangles like this. Infinitely thin horizontal rectangle might look something like this. And you can see all the way from the bottom to the top, the line is the right boundary and the curve is the left boundary. So I only have to set up one integral for this. So how do we set the integral up? Let's get down to that. Let's see, we've got everything we need now. I can erase all of this. Okay, so in this case, if I look at the area of that rectangle, the height, or the width of this is dy because it's a vertical change. So the width of this is dy. And I need to multiply that by its length to get the area. So what I need to take my right x value, so I'll put a subscript of r on this guy because that's my right x value, minus my left x value. And they need to be in terms of y. So my right x value in terms of y is 1/4 y plus 4. minus my left x value to get my length is going to be 1/4 y squared minus 1. And that's the length of that rectangle. So this entire expression represents the area of that rectangle or any rectangle in the region. Now I just need to add all of those infinite areas together from y equals -4 to y equals 5. Again, I know I have to use y values here because this is dy, and everything's in terms of y. So there we go. We've done the hard part and set up the integral to represent the area of this region. This one's different than the last because we used horizontal rectangles. We used functions written as x in terms of y, which is kind of unusual if you've never done it. Practice with those xy tables. I'm going to pause the video and work this integral out so you can check your answer. Come back to me. Okay, when I evaluate this integral, I get 30.375 as a decimal. One cool thing that I might point out to you if you're interested is I didn't like the fractions here, the 1/4. So what I did was I factored out this -1/4, which made all of my coefficients integers and made my integration a bit easier now. Not terribly easy because I still had all of these fractions to deal with, which I went ahead and let the calculator deal with. But anyway, that's what I get to be the area of this enclosed region between those curves. All right, let's look at another example using trig functions because everybody is scared of trig functions. All right, so let's calculate the area of the region enclosed by y equals the sine of 2x and a similar function y equals 2 times the sine of x. Okay, so I chose this example because I figure some might be interested in the trig functions. We'll also see a trig identity that you may have forgotten. We'll also see how to solve a trig equation. So lots of good stuff in this example. So the first thing, like anything else, is before we start graphing, it might be good to find the intersection of these two curves. Luckily, they're already solved for y. They both are. So all we have to do is figure out where the sine of 2x equals 2 times the sine of x. So we're trying to solve this trig equation for x. What x values make the sine of 2x equal 2 times the sine of x? And so the first thing you might want to do here, you might remember from trigonometry or pre-calculus, is it'd be easiest if the arguments of the trig functions were the same. So this argument's 2x while this argument's only x. So that's a hint that on the left side we want to use the double angle formula for sine. The sine of 2x, if you remember, is the same thing as 2 sine x cosine x. And you want to make sure you do remember those because when you get to calculus 2, you'll use those trig identities a lot. Equals 2 sine x. And so now you can see the sine argument is x, the cosine argument is x, and the sine argument is also x. That's a good thing. Let's go ahead and divide both sides by 2 to make it simpler. And then just like a quadratic equation, let's get 0 on one side and then factor. So what we'll do is we'll subtract this sine of x over. So I get sine x cosine x minus sine x equals 0. And then these two terms have a sine of x in common that we can factor out, leaving cosine x minus 1. Now to finish solving this, if I've got two factors that multiply to be 0, then one of those two factors has to be 0. So the conclusion we can make is that the sine of x has to be 0, or that the cosine of x minus 1 has to be 0. In other words, cosine of x could be 1. So what angles could x be? What angles could x be so that the sine of x is 0? And that reminds me, in fact, I forgot to put a little extra condition into the problem. We're only going to look at this because the sine waves go on forever. So this, as we say here, the area is infinite because there's an infinite number of enclosed regions. But I meant to say we're only going to do this for x values between 0 and pi. I'm sorry, I forgot to write that. So when we're looking from 0 to pi, where is the sine function equal to 0? Well, that's true whenever x is 0 and whenever x is pi. So there's two angles from 0 to pi where the sine of x is 0. Cosine of x is 1 whenever your angle is 0. And so this doesn't actually give us another point of intersection. We've already got x equals 0 over here. So we've got 2 points of intersection. One occurs at 0, one occurs at pi. Now, we could certainly set up xy tables for both of these. And if you did, it would look something like this. You'd want to go from 0 to pi. And so you might look at pi over 2 halfway in between. Then you might look at the pi over 4s, 1 pi over 4 and 3 pi over 4. And you could calculate the y values. However, these are very simple sine functions. So I'm not going to take that approach. The sine of 2x function has an amplitude of 1 and the period is shrunk by a half. So it's squished. If you graph that, let's set up our plane. We're only going from 0 to pi on the x-axis. So here's the x-axis. Let's say that this is 0. And let's say that this is pi. Okay? Only going from 0 to pi, and we need to graph both of these functions. Now the sine of 2x function has an amplitude of 1, while the 2 sine x function has an amplitude of 2. So I want to make sure that I get that amplitude of 2 included. So 1, 2, 3, 4, 5, 6. Here's negative 2. And then sine of 2x has an amplitude of 1, so I'll mark 1 as well. Okay. All right, so we've got our grid set up. We could identify pi over 2 here, in fact, if we wanted. So pi over 2 looks like it's right here. And we could cut that in half again if we wanted to. So something like this. Okay, so we've got our grid set up. Now we need to graph the two functions. So let's graph the sine of 2x function first, which has an amplitude of 1. Well, the sine of 0 is 0. And typically, sine doesn't get back to 0 until it gets over to pi, but it's squished by a half. So it's going to get back to 0 right here at pi over 2. And in between those 2 points, it's going to hit its highest point at 1. Right? The sine function comes up and then back down. And then after that, it drops below the x-axis down to negative 1 and then back to 0 at pi. So this is the sine of 2x function. I have a hard time drawing this. All right, so that's the sine of 2x function. Now let's graph y equals 2 times the sine of x. Well, this guy's not squished, so this guy's going to go from, it's going to start at 0 and not reach 0 again until it gets over here to pi. And those are, in fact, the 2 points of intersection where the two curves hit. So both curves hit those points. The difference is the 2 times the sine of x function is not going to go through a full wavelength here. It's only going to go through half of one because it wasn't squished. So it's going to reach its highest point of 2 in the middle here at pi over 2. So it's going to look like this. Okay? And so basically it's going to do this sort of thing. It's just going to be the first half of a wave, but it's going to have an amplitude of 2, and it's going to take a whole pi interval to go through half of that wavelength. And so these functions both continue on forever, but we're only interested in this portion, and now we can see the area that we want, which is this area here. Kind of a cool little geometrical figure. We also want to make sure to label both functions. So the curve that's on top is y equals 2 sine x, while the curve that's on bottom is sine of 2x. Okay? So that's good. Now we can work towards evaluating an integral that will give us that area. Okay, so we need to imagine where we would cut this with a rectangle, and since the y equals 2 sine x function is always above the other, let's use vertical rectangles because the height's easy to calculate. Grab the right marker here. So anywhere in this region, a vertical rectangle is going to look something like that, okay? And so if we go to set up our integral, the width of that rectangle is a horizontal distance, so it's dx. The height is going to be the top y in terms of x. Well, the top y is 2 sine x minus the bottom y is sine of 2x. So we have 2 sine x is our top y minus sine of 2x is the bottom y. And that's the area of that rectangle that we see there. And we need to add all of those areas together, so an infinite sum. We're looking for x values for our limits of integration, and this occurs from x equals 0 to x equals pi. And so this integral represents the area of this enclosed region. So that, again, is the hardest part. However, this integral maybe is not that simple to calculate. So what I'm going to do here is get you started, and then I'll pause the video to finish it. So the best way to start this guy is going to be to split the integral apart. So take this integral minus this integral. And in fact, when we do this, we're going to factor out that coefficient of 2. So we've got 2 times the integral of sine x dx minus the integral from 0 to pi of sine of 2x dx. Now the reason I'm splitting these apart is because I know the antiderivative of sine of 2x, or sorry, sine of x. The antiderivative of sine of 2x is not quite as simple because it involves inversing the chain rule because the input is 2x. It's a function within a function. So personally, I could do this integral no problem, but at this point, based on where the examples we're doing, you probably need to use substitution to evaluate this definite integral. So that's how I'm going to work it up here. I'm going to pause the video. You can try it out too, and then come back and check your answer. All right, so what a fantastic example. Lots of interesting stuff going on here. Just to get to the answer, the area of this region enclosed by these two crazy trig functions with this odd shape is 4. We're not rounding or anything. It's exactly 4. How fascinating is that? Now back here on the substitution, you can see how I laid that out here. So it's interesting to see that I evaluated this first definite integral all in terms of x and got a number, whereas the second definite integral I evaluated all in terms of u and got a number. You can do that, no problem, because they're 2 independent integrals at this point. Now something I want to point out, I'm not going to run through the whole thing, but the antiderivative of sine of x is negative cosine x, but you see I have positive cosine x here. I just factored that negative out to be part of my coefficient, so I wouldn't have to deal with it in here. And the same thing here, when I did the antiderivative of sine, I got negative cosine, but I pulled the negative out and changed this negative to a positive. So I just wanted to point that out. All right, let's finish it off with the grand finale, look at one final example that's very interesting, and I'll be right back. Okay, so I saved this example for last because we're actually going to look at regions enclosed by 4 curves. Now don't be scared off by this. We have just a basic parabola, a slanted line, and 2 vertical lines. So really it's hard to even count those as being part of the problem, but they do impact the solution. So they are significant, but they're very simple to deal with. Now to save a bit of time, because we've done it so many times so far, I'm just going to graph this by plotting points. Okay, so let's start with the parabola here, and I'm assuming we're going to go from -2 to 3 on the x-axis. So let's set that up, and just I've already done this in preparation for this video, so I kind of know what to expect. So just follow along here. So let's say this is -2, and then we've got sorry, maybe I can count by ones, right? -2 followed by -1, and then 0, 1, 2, and 3. So here's our y-axis. Okay, and I need to go down to -5, it looks like. So this will be -1, 2, negative 1, negative 2, 3, 4. Here's negative 5. So here's negative 1. Clearly a different scale in the x and y axes. So 1, 2, 3, 4, and there's 5 on the positive y-axis. So let's graph the parabola first. If I plug in negative 2 for x, I get 4 minus 4, which is 0. Switch colors here. 4 minus 4 is 0. If I plug in negative 1, I get 4 minus 1, which is positive 3. If I plug in 0, I get 4. If I plug in 1, I get 3. And if I plug in 2, I get 0. Those are easy to see because of the symmetry. If I plug in 3, I get 4 minus 9, which is negative 5. And here is the parabola. I don't know why I torture myself with making myself draw these on video, but there we go. That one came out pretty good. So now let's graph the slanted line over the same negative 2 to 3. So if I plug in negative 2, I get negative 2, which is positive 2 plus 2 is 4, which is up here. And really, because it's a slanted line, I really only need one other point. So I'm going to go all the way over to 3. Negative 3 plus 2 is negative 1, which is here. And so I can connect those with the straight line, hopefully. I'll be very careful here because it's going to yield my points of intersection without doing any algebra. Yeah, something like that. And so there's our line. Okay, no problem. And then I've got the vertical line, x equals negative 2, which is this line right here. And x equals 3, which is this line right here. And so if we analyze this graph, we've got 3 regions that are enclosed by these guys. So we've got one region here, one region here, and one region right here. Okay? So we're going to have 3 integrals to calculate the total area. So we need to evaluate rectangles in each. Let's go ahead and label the functions. So the parabola, so in the first region, the parabola is the bottom, right? So I'm going to label it down here, y equals 4 minus x squared. And on top, I get y equals negative x plus 2. And then they switch places over here. So now my top is y equals 4 minus x squared. And my bottom is negative x plus 2. And then they switch again, where the top is negative x plus 2, and the bottom is 4 minus x squared. And luckily for us, in all of these regions, we can see that vertical rectangles are going to work great, because in this region, the entire region, the line is the top. In this region, the parabola is the top and the line's the bottom. And in this region, the line's the top and the parabola is the bottom. So I can use rectangles, vertical rectangles, for all 3 integrals. So to set it up, in the first region, we can see the point of intersections very nicely. They hit lattice points, so very clear what they are. So my first integral, the width of my rectangle is dx. It's a horizontal measurement. Times the height, which is going to be my top y, in terms of x, which is negative x plus 2, minus my bottom y in terms of x, which is 4 minus x squared. That's the area of the rectangles in the first region. Then I need to add them all together. Look at my x values. They go from negative 2 to negative 1. So this integral is the area of the first region. Then I need to add to that the area of the second region, which now is going to go much quicker. It's an integral from negative 1 to positive 2. The top y is 4 minus x squared, minus the bottom y is negative x plus 2, and the width is dx. And then I need one more integral from 2 to 3. The height is the top y, negative x plus 2, minus 4 minus x squared, the bottom y, times the width, which is dx. And so you can see when you go to do this problem, you're going to have to evaluate each integral, and you're going to be doing the same antiderivatives over and over and over again. So you might do them once and then reuse them multiple times when you actually work the problem. Now this time, I don't have a lot of board space, so I'm not actually going to work out these basic integrals, okay? But it should be pretty simple. The hard part is going from the words to the graph, intersection points, converting your graph to rectangles to integrals, okay? And so I hope through all of these examples and all this time I've spent that you're able to follow along with what's going on and that you have great success when you go to do it on your own. Good luck.